In this video, we're going to go over rotational kinetic energy and rotational momentum. This is going to be our final video of the rotational unit. So we're going to find the rotational equivalent of both momentum, kinetic energy, and the impulse. In the first few minutes, we're going to go all the equations that you guys need to know and what do they mean and where do they come from. In the next few minutes, we're going to go over a step-by-step instruction how to approach the conservation of angular momentum problems. And in the rest of the video, we're going to solve one practice problem that is going to teach you how to apply these steps. So by the end of this video, you should come up with a really good understanding of what is the rotational kinetic energy and what is the rotational momentum when it is conserved. Let's start by looking over our formulas. So first we have a formula for rotational kinetic energy, which is just going to be an equivalent of linear kinetic energy, right? As you know, the mass becomes moment of inertia and linear velocity becomes angular velocity here. So we have a formula that looks almost the same as the linear one, just as the rotational equivalent. Similarly, we have a formula for rotational momentum, which is a rotational equivalent of the linear momentum. So for linear momentum is mass times velocity. So mass becomes moment of inertia, I, and velocity becomes angular velocity, W, or omega, sorry. Then remember, when we were talking about momentum, right, we were saying that if you apply an external force over some unit of time, you can actually change momentum, right? So you can make the object move faster or slower. Therefore, if you apply the rotational equivalent of force is torque. So if you apply some kind of torque, you can change the angular momentum as well. So we have a rotational impulse as well. Now, also in other important formulas that I bring up in every rotational video are these ones. How to convert from linear velocity, displacement, and acceleration to rotational velocity, displacement, or acceleration by basically multiplying this by radius. Now, final formula that I will derive. So all of these formulas so far should be on your equation sheet, but this final one will not be. It's just another way. So we're going to derive another formula for angular momentum. Now, angular momentum is I times omega, but remember, for point masses, moment of inertia is just mr squared. So I'm going to plug this for I. And omega from this formula right here, omega is equal to V over R. So I can plug this in here. So radius cancel out and I have mRV, another formula for angular momentum, which is going to be important to keep in mind as we're going to solve some of these problems. Now, in our first example, we will assume that momentum is conserved, right? So there's not going to be impulse or any external torque. When momentum is conserved, we have our conservation of momentum method, right? That applies here. It's the same exact method that we saw in the linear motion, right? The steps are going to be exactly the same. They're just going to be applied in the rotational framework. So first, we always sketch the problem, right? We represented the initial and final moments. We labeled the moments of inertia and angular velocities omega. So basically sketch the problem, write down all the i's, all the omegas given. Then we calculate total initial momentum by adding all the momentums of the objects involved. We calculate the total final momentum. So if there's multiple objects, we sum all of them up together and we just set them equal to each other, right? And solve for the unknown. Now, with this in mind, let's take a look at one of our practice problems. So here we're going to have a rotating disc that spins freely with an angular velocity of 800 revolutions per minute around a horizontal axis of negligible friction. Suddenly, a second disc, which has a moment of inertia twice that of the first disc. So let me kind of do a diagram, right, of the initial situation and the final situation. So the second one has the moment of inertia twice that of the first disc. So it has 2I. So the final situation, we have the moment of inertia of the first disc, which is I, and the moment of inertia of the second disc, which is twice that of the first disc, 2I. So the total moment of inertia is 3I, and their final velocity is unknown. That's what we need to find. Great. Due to the friction between them, the two disks quickly synchronize to rotate at the same angular velocity. So we need to find firstly the new angular velocity on the system. So the angular momentum here is going to be conserved. So initial angular momentum is equal to final angular momentum. The initial angular momentum is going to be just consist of the first disk, so W times I, and the final angular momentum, now they're rotating together, so it's going to be 3I times omega f, final velocity. Now I here cancels out. The initial velocity, right, is 800 revolutions per second and 3 WF. So the final rotational velocity is just going to be 800 over 3, or 266.7 revolutions per minute. In this case, I didn't need to really convert this to radians per second, although you totally can. It's just that it wasn't really necessary to solve this problem. So a pretty straightforward problem, as you see, right? We just plug in for initial angular momentum and final angular momentum and pretty much solve this. Now, in part B, they're asking us by what factor did the kinetic energy of the system decrease? So let's take a look. As you remember, nothing says that kinetic energy has to be conserved, right? So the total energy in this problem will be conserved, but the rotational kinetic energy will not be. So the initial kinetic energy is 1/2. Let's take a look at our initial thing. 1/2 I times, let's say, omega squared. Great. What about the final kinetic energy? So final kinetic energy is going to be 1/2. So your new moment of inertia is 3I. And your final velocity, as you remember from here, right, it was just in terms of letters is W over 3. So it's going to be, so that's our final velocity, right, is 1/3 that of initial squared. So here we have our final velocity. Let's just simplify this a little bit. So this will be 1/2 times 3I. Now I have to apply the square to both of these terms. So it's going to be omega squared. 3 squared will be 9. So 3 over 9 is going to be 1/3. So 1/2 times 1/3 is going to be 1/6 I over omega squared. So they're asking us about what factor did it change. So essentially all we have to do is divide the final over initial. So 1/6 I omega squared divided by 1 I omega over 2 divided by the initial kinetic energy right here. When we divide, we multiply by reciprocal. So let me rewrite this as I omega squared over 6 times 2 over I omega squared. These terms cancel out and we have final answer of 2 over 6 or 1 over 3. So essentially our kinetic energy decreased by a factor of 1/3. Great. In the next problem, we're going to go over a more advanced problem on the conservation of momentum. And we're also going to go over one problem when the momentum is actually not conserved. Both of those problems will be very important and very representative, so I really encourage you to watch that video. Other than that, keep watching these videos, keep practicing on your way to an A. Thank you guys for watching.